Hey everyone, in this AP Chem series video, I'll explain the theory behind photoelectron spectroscopy. First, remember that successive ionization energies refers to the energies required to remove one electron after another from the same atom. So on my carbon atom, if I removed one electron and measured the energy it took to do it, I'd be measuring the first ionization energy, or the second, or the third, and so on. And you can see all sorts of patterns in doing this, like that it takes more energy to remove inner shell electrons compared to the valence ones. In this video, however, we'll ask a different question, which is how exactly can you measure these values? And of course, one way that you can measure these ionization energies is with something called photoelectron spectroscopy, or PES for short. The first step to doing PES is to get yourself a photoelectron spectrometer. That's the name of the instrument itself, and it looks something like this. Next, you would get some atoms to inject into the spectrometer, and with the help of a computer, it would produce something called a photoelectron spectrum, which you would then analyze in order to determine the ionization energies of the electrons in those atoms. So let's explain some of the theory that goes on behind the scenes with PES in order to understand how it works. So the first thing my photoelectron spectrometer is going to do is generate some extremely high energy X-ray photons, and it's going to do it in such a way that it knows the exact energy of each of these photons, and it's going to collide them with the atoms in the sample. So let's say we inject some beryllium atoms into the photoelectron spectrometer. They're going to get bombarded with X-ray photons, and let's just say in this case those photons have energies of 143,000 kilojoules per mole. So those X-ray photons are actually going to collide with the electrons of the atom, and as they do so, they're going to cause them to be ejected, or essentially removed from the atom. Once the electron has been removed or separated from the atom, it is now referred to as a photoelectron. The instrument then measures the exact speed of these ejected photoelectrons, and from that speed we can calculate the kinetic energy of the electrons themselves. In this case, the ejected electron has 132,000 kilojoules per mole of energy. So notice that my X-rays came in with 143,000 kilojoules, but my ejected photoelectrons don't have all that same energy. In fact, they have less. So that means somewhere along the way, energy was lost. And that lost energy was the energy that was needed to break the attraction between that electron and the nucleus. In other words, the difference in the two energy values is equal to the ionization energy of the ejected electron. Here's the math behind how it works. We started with 143,000 kilojoules of initial energy. If you subtract out the energy that's left over for the photoelectron, you can calculate that 11,000 kilojoules was lost in the process. That's the energy that was used to eject the electron, or otherwise known as the ionization energy. This is a pretty nice summary of how PES works, so make sure to take some time and write it down. So we just determined the ionization energy of the electrons in this outermost shell, but if we kept bombarding these atoms with more X-rays, the X-rays would remove multiple electrons from many different atoms in the sample, and we could calculate the different ionization energies for all the electrons in all the different orbitals that the atoms have. So eventually some of the X-rays might collide with these inner electrons and eject them. Measuring their speeds, we'd calculate that they have 125,000 kilojoules per mole after being ejected. Remember, for the first electron removal, it took 11,000 kilojoules out of the initial 143,000 to eject this electron. Well, here there's even less energy left over. If you subtract it out, you'll find that that's because it took 18,000 kilojoules of energy to remove this inner core electron. So now we know the ionization energies of electrons in the first and second energy levels. That also wraps up this video on photoelectron spectroscopy theory. Here's a brief summary.